Hi everyone, I am going to explain about one important feature, that is latch up in CMOS circuits. So what do you mean by latch up? What do you mean by latch up? Latch up is nothing but existence of a low resistance path between VDD and VSS. Existence of a low resistance path between VDD and VSS. This low resistance path is existed because of the, what is the reason? Because of the existence of virtual devices like transistors and resistors. Okay, so before going into the concept, let us see the definition of latch up. Latch up is defined as the existence of a low resistive path between VDD and VSS. This is possible with the help of what is the reason for this one? Virtual transistors and resistors, which are the properties of the materials which we are using in the creation of the CMOS device. Okay, this is what the latch up. Latch up is nothing but it is defined as, what do you mean by latch up? In existence of low resistance path, between VDD and VSS. If there is any such resistance is existed between VDD and VSS, then definitely there exists a static current flow. This leads to static current flow. Static current flow from VDD to ground. Okay, so we can say this is a problem. We can say latch up is a problem in the CMOS circuitry. Suppose I will tell you one device called SCR. SCR is nothing but silicon control rectifier. It is a three terminal device. SCR is a three terminal device, or we can say it is a silicon control rectifier. The symbolic representation of the silicon control rectifier is this one. So here is the place where we are applying the gate signal, and it is the anode and it is the cathode for the symbolic representation of the silicon control rectifier. If you see the internal architecture of the silicon control rectifier, it will be having four different regions that are P, N and again P, N. So P, it is having four different regions where the anode is taken as P terminal and cathode is taken as N terminal, and the gate terminal is connected to this P. Gate terminal is connected to P. Suppose if you just divide this, so if you just divide this, then it also N, it is also P. So we are writing separately that diagram. So you can write it as, redraw it as P, N, P. And one more is N, P N. So this N and this N are interconnected, and this P are interconnected, and whereas this anode terminal and a cathode terminal, we don't have any other terminals, only two terminals are here, and one more is gate terminal that is connected at this point where we are applying some gating pulse at this particular P. Okay, so PNP is a transistor and NPN is a transistor. So we are having two PNP and NPN transistors. So take this transistor which is a PNP transistor. Sorry, it is a PNP transistor. It should be like this. So PNP, and the other transistor is like this, where N connected together. This is the N terminal and this P terminal, and this is the N terminal where the P terminal is connected to this P terminal. Okay, this is what the structure that we have with respect to the silicon control rectifier. Now the same will be applied with the help of the latch up. The same circuit diagram will be the equivalent circuit for the latch up problem in the CMOS circuit. See here, we have a CMOS circuit here, okay, where we have considered a N-well process. See here, this is N-well, which is fabricated or insert diffused at the P substrate. So first initially we have taken a P substrate, later N-well is diffused, and later we have gone for the diffusions of individual P and N plus regions. Okay, so once everything is ready, then what happens? See here, this is a P region. So P type, and the substrate is of N type, and again the other terminal is nothing but P substrate. So PNP transistor is created at this particular point. And similarly, this is N plus region, this is N plus region, and in between we are having a transistor that is again NPN transistor. Its base is connected to this collector terminal. Okay. Additionally, we have two substrate resistors. So one is this N-well resistor R-well, and the substrate resistor is noted as P substrate. Okay, and of course we know already the connections how they are made. Now if you draw the equivalent circuit diagram of this one, this is the equivalent circuit diagram where we are having the two NPN and PNP transistors connected back to back. Additionally, R-well and R-sub. See, if you see the R-well resistance which is connected from VDD to the base of this transistor, R-well. See here, we see VDD where we are having power supply VDD, and then let's say resistor is connected to the base of this transistor, base of the transistor, which is nothing but PNP transistor. Okay, and next another resistor R sub is in between VSS and the input base of the transistor. This is here, this is here. So now when you are just redrawing the entire circuit, it will be appear like this with a common closed loop where the transistor and two transistors and two resistors are connected in different directions. So because of this, what happens? Because of this existence of unnecessary components, virtual components, the original behavior of the CMOS inverter will vary. Original CMOS inverter operation will be varied. That means how to avoid this? Okay, we are saying that it is a problem. It is a problem. What is the solution or remedy for this one? Latch up problem. So the to avoid latch up, problem in CMOS, the first one is reduction of substrate resistance. Reduction of substrate resistance. And the second one, reduction of N-well resistance RW. Substrate resistance is nothing but R sub. Reduction of N-well resistance. Okay, so N-well resistance, reduction of the N-well resistance, which is nothing but R well. As we have two resistors, these two resistors can be reduced to reduce the effect of the latch up. Another one is the reduction of RS and RW, means that a large lateral current is necessarily to invite latch up, and a higher value of the holding time is also required. Okay, so the parasitic PNP transistor, which is a part of the N-well latch up circuit, has its beta reduced owing to its presence of the buried N plus layer. This has this effect of reducing carrier lifetime and the N base regions, and this contributes the reduction in the beta. And a few other methods are also there, which is nothing but guard rings for all the substrate and dopings. Okay, suppose if you go to this diagram, the transistor is created only because of the existence of three different regions like N, P, N. But if you provide a guard band at this particular region, here also if you provide any guard band, then there will be no action of the resistance that is created between them, and transistor operation will also violate. Okay, so guard rings for all the substrates and as well as dopings can be created so that the guard ring will avoid the effect of the latch up or the creation of any unnecessary active or passive devices in the CMOS circuit. Okay, so these are the main important points to be discussed to avoid the latch up in CMOS. Okay, thank you.